Since we now know the basics of Karnaugh maps and their relationship to truth tables as well as the sum of products min-term form, we're going to go ahead and do a bunch of examples of 2, 3, and 4 variable functions so that we can see how to better use the Karnaugh map. To start, let's do a few 2 variable functions. Now, just to save time in the video, I've drawn a bunch of this stuff out ahead of time so that we can get right down to the big business. So here in the top left, what we can start with is this sum of products min-term form expression that says min-terms 0 and 2 on a 2-input circuit have 1s. So the truth table for that would look like this. Here's row 0, and here's row 2. So we draw a 2 by 2 Karnaugh map so that it has 4 cells for our 4 min-termed function. And then we label the 2 dimensions A, B, and their values 0, 1, 0, 1. And I won't repeat that for every one of these, but I want to make sure we do it at least once. Now each cell, as you'll recall, is the intersect of the different variables on each dimension. So this cell down here in the bottom right is when A is a 1 and B is a 1, which is the 2-digit number 1, 1, or 3. So this is the cell for min-term 3. So here's the cell for min-term 0. Here's the cell for min-term 2, each of which should have a 1. Everything else has a 0. Now what we'll do is ones looping. And if you recall, to do the ones looping, what we need to do is draw rectangles around only ones. And we want to make sure that those rectangles have an area that is a power of 2. And every single one has to eventually be covered by some rectangle. And we want to use as few very large rectangles as possible. Now, that's all going to be very easy in 2 input functions because we have so few patterns to even work with. So in this case, we're going to put a rectangle here. And so its area is 2, which is 2 to the first, so it's a power of 2. Now all the ones have been looped, and we can go right to writing down what the simplified version of this expression would be in a sum of products form. So we'll say that x is a function of AB and is equal to, well, what's the pattern for being inside this rectangle? Start with A. Since sometimes it's 0 and sometimes A is 1, A is of no consequence here. So all that matters is B, and B is always a 0. So we would just say that this function is B with an inversion bar. We want B to be 0. For the next one, I'll go down here, I guess. On the bottom, we have another 2-input function, this time with min-terms 0, 2, and 3. So this is the space for 0. This is the space for 1. This is 2, and this is 3. So our 1s are there, and this is what the equivalent truth table will look like. So again, I want to group these in rectangles. So here's one rectangle I can see because it's just like the other one. But I still need to get this one somewhere. So I could put a rectangle around it, but remember that one of the rules, or rules of thumb, is not only do we want the rectangles to have an area that's a power of 2, and 1 is a power of 2, we want these rectangles to be as big as possible. And the reason is, if we just picked this in a red loop, that's going to be when A is a 1 and B is a 1. But if we instead make that rectangle big, like this, now B is 0 or 1, which means B doesn't matter for this rectangle, and so we'll get a simpler product. All right? So that means we have, I'm getting all my pens mixed up. That means we can say that Z, which is a function of A and B, is equal to, blue one, B is 0, and that's how we get in here. So B inversion bar. And for the red one, A has to be a 1. So inverse of B or A. Not so bad. All right, let's do it for the exclusive OR function at the top, which we'll call Y for whatever reason. I just wrote that there. I didn't feel like erasing everything or redrawing this page. I should have just kept with exclusive OR, but we're calling it Y. but it is the exclusive OR function. And here we have minterms 1 and 2, are the only ones that have a 1 in output. So here's cell 0, 1, 2, and 3. So 1 and 2 both are highlighted. Now, even though these are connected to each other diagonally, they aren't connected in such a way that I can draw one rectangle that encompasses both of them and not any of these other zeros. So in this example, unfortunately, I will need 2 loops that just go to each of these individually. And that happens sometimes where we have a 1 or a couple ones that we can't loop together with something else. So now that really means we end up with this y function, which is really exclusive OR. And we'll say that for this red one, a is a 1 and b is a 0. A is a 1, b is a 0. Or a is a 0 and b is a 1. Just like that. Okay, let's look at some 3-input functions. We'll get a little more exciting here, and we'll start incorporating some new stuff. Like instead of just having arbitrary functions, we'll say we have a function with purpose. So on the left, we're going to start with this. Let's create a function x, a circuit x, and its equivalent Boolean expression, simplified. That'll be a 3-variable function, so a, b, and c. And what we want it to do is produce a 1 on output whenever this 3-bit input has 2 1s in a row, and we'll include wrapping. So here I've marked, here's 2 1s in a row, so this minterm will get a 1. Here's 2 1s in a row, so that'll get a 1. And there's 3 1s in a row, so this will get a 1. But with wrapping, this one, minterm 5, will also get a 1. Everything else gets zeros. So that's the same thing then. We could go from here to immediately making this truth table. And we can go from the truth table to this sum of products minterm form expression, where we've got rows 3, 5, 6, and 7 having 1s. So now we need to fill in our 3-variable Karnaugh map. Remember that when we go to that third variable, the horizontal dimension just doubles in size, and we have to number it with a 2-bit value. And as we move from left to right, we can only change by 1 bit. So it goes 0, 0, 0, 1, and then 1, 1, not 1, 0. 0, 1 to 1, 1, and then 1, 0. And that keeps that's our gray code, and it keeps the nature of the Karnaugh map in check for us. So let's see, I need cell 3 to have a 1 in it. So here's 0, 1, skip over to 2, and come back to 3. Okay. 4, 5, skip over to get to 6, come back 1 to get to 7. Everywhere else is going to have zeros. All right, so let's see if we can't do the ones looping on this. Now there's a nice big row of 3 1s, block of 3 1s together here at the bottom, but I can't put a rectangle around them because the area of that rectangle would be 3, which is not a power of 2. So I'm going to have to do this kind of in overlapping chunks. So there's one rectangle, as big as I can make it, while maintaining a power of 2 area. And there's another rectangle, as big as I can make it, while maintaining a power of 2 area. Now I want to do the same thing for this top one, but I have the exact same problem. So I'm going to overlap again this way. And that means with 3 loops, I'll have 3 products in my resulting expression. So now I can say that x, which is a function of a, b, and c, is equal to, let's do the blue one first, these 2 1s, a has to be a 1. So a regular, no inversion bar. For b is a 0 here, but for this one it's a 1. So b is of no consequence. We'll eliminate it. C, on the other hand, is a 1 in both columns, so we need a regular c. Let's do the red one now. We OR it with the product from the red loop. Let's see, a still has to be 1, so that's good. B is also a 1 in both of these positions. But C goes from 0 to 1, and since it differs within the same rectangle, we eliminate it. Let's do the last one here, the green one. This time we have A is a 0 in the top one, and A is a 1 in the bottom, so A is out. And it looks like B and C both have to be 1s. So B and C. And there we have our simplified sum of products for that function. Now let's do this function y. So this again is going to be a 3-variable function, and what we want to do is produce a 1 as output if the 3-bit input is an even number less than or equal to 4, or, I should say, or it's an odd number greater than 4. So even numbers less than or equal to 4 are 0, 2, and 4. And odd numbers greater than 4, at least for a 3-input function, are going to be 5 and 7. We only have 8 values from 0 to 7, so we can't go past 7. So see, for this, I didn't even need a truth table. I could go right from the description to this form. And I can go now from this form to filling out the K-map. So let's see, here's cell 0, I get to 1. 0, 1, skip over to 2, come back to 3. The next row is 4, here's 1, 0, 0, so there's 4. 1, 0, 1, there's 5. 6 is over here, and come back for 7. 1, 1, 1. Yeah, that's 7. So everywhere else is a 0. All right, now we got to do our looping. I'll start with this one that's sitting right here. Again, I see 3 1s in a row, but I can't put a rectangle around an area of 3, so I'll have to stick to 2. There's 2. That's pretty good. Now, I got to get, well, I can do this as a column. That's good. So there's 2 loops. And then with a third loop, I can get this last one. But don't forget that these Karnaugh maps wrap torally, horizontally, and vertically. So instead of doing a small loop of area 1, I'm going to do a loop that wraps. That's twice as big as an area of 2. And that will reduce the size of my product. All right, so that means we now have y as a function of a, b, and c equal to, let's do same order, blue one first. For both of these ones, a is a 1. B is a 0 or a 1, so it doesn't matter, we'll get rid of it. And C is a 1 in both cases. So A, C. Ordered with red rectangle. A is a 0 or a 1, so it doesn't matter. And B and C are both zeros. So B inverse for 0, C inverse for 0. And then we'll OR that with the green loop. Let's see here. A is a 0 in both cases, so inverse of A. B is a 0 here, and for this one, B is a 1. So B's out. C is a 0 here, and C is a 0 here, so C is a 0. And we've got our function figured out. All right, now let's do some size 4. 4 variable functions. I'm going to get wacky on this one just because we want to have fun too. So on the left, here I just wrote a sum of products minterm form expression. And I just picked some numbers that were between 0 and 15 since those are the minterm rows we have. Let's fill them in. Now remember in this one, not only do we have the gray code order horizontally, but we also have to have it vertically. So we go 0, 1, 3, and then 2. 0, 1, 3, and then 2. So we'll have one row, another row, then we'll skip a row, and then come back a row if we were counting in order. And in each row you go first, second, third, and then fourth. All right, so let's fill in these numbers with 1s. I need 0, that's here. Here's cell 0, 1, skip over to 2, we need a 1 there. Come back to 3. We don't have that up here, so we'll put a 0. 4 is here, Doesn't show up in my expression, so I'll put a 0. 5 is here, so we get a 1. Skip over to 6, come back to 7. Now skip a whole row because of the gray code. And now we've got 8, 9, 10 is over here, 11 is back here. Fall back a row to 12, 13, skip over to 14, and come back to 15. All right. So these other cells are all 0. So this is definitely more interesting just because it has more variables. And of course, more variables can exist in a function. They're just harder to do with the Karnaugh map on paper because we have to start drawing hyper rectangles, three-dimensional ones or beyond. So let's see what we can get here. I immediately see a big cluster of 4 right here. Big tall line of 4, and that is good because 4 is a power of 2. I also see interwoven with it this group of 4. And that's good because 4 is a power of 2. Then over here, I can see, well, there's more than one way to do this, I guess, but I'm seeing this particular one could either be grouped in a group of 2 with this one or in a group of 2 with this one. I'm going to arbitrarily pick this one. Either would have been fine. And then for this guy, there's also several ways we can deal with this. First of all, I see I can group him with this, so that would be a rectangle of 2. But because of wrapping, I can do these 2 and these 2 in the same block of 4, and that would be even better. But there is another block of 4 that this is a member of. Because of the wrapping, again, works horizontally and vertically, you can get all 4 corners into the same group of 4 as well. But I think what I'll do, since I can pick up these 3 all at once, is I'll group those like this. And don't forget, it is possible to do all 4 corners in a group of 4. All right, so let us then figure out what our simplified expression is. It's going to be x is a function of a, b, c, and d, and is equal to, let's do the tall green one first. A and b clearly don't matter because it goes all the way up. So c and d have to be 1 and 0. So c is 1, d is 0. Or, blue square, let's see, what do we got? For these 2 rows, the only thing that stays the same is b. It's a 1. So b is a 1. For these 2 columns, the only thing that stays the same is the 1 in c. So this is b ANDed with c. A and d don't matter for that part. Let's do the other small blue rectangle. A needs to be a 0 to be in these 2 positions. B doesn't matter because it changes values. C and D both stay the same, 0 and 1, because it's just one column. So we need a 0 for C and a 1 for D. Yep, that's good. Then we have the red one left. And so, or that with the red one. And the red one, in these 2 rows, A changes, so it's useless. But B stays 0. So we have inverse B. In these 2 columns, C is a 0, but D changes value. So we want C to be a 0. And there we have it. We've got a nice simplified sum of products expression for this using a Karnaugh map. All right, so for our last one, we'll have the most fun and hope that this turns out some meaningful way. So this is going to be our kind of soft rock circuit called Y. It's a 4-input circuit. And the basic idea is we love that song, Jenny, which I cannot remember the name of the band off the top of my head. It's not really a favorite song of mine or anything, but it sure is catchy. And so basically any of the min terms that come up that are in her phone number, we want to have a 1 come out of that circuit. And we want to say otherwise 0. But because this is our soft rock circuit, not only do we want 1s here and 0s otherwise, but we're not really that into AC/DC. So what we're going to say is that this circuit is going to be connected in such a way that it'll be impossible for either the product AC or DC to even happen. So we'll have to find minterms that map to this expression and cross them out with an X, because they're impossible. Unless, of course, it's one of the minterms from Jenny's phone number. So let's start with Jenny's phone number. 0 happens first, that's here, 0, 0, 0, 0. So there's a 1 there. 3 is the next, that is, let's see, 0, 0, 1, 1 is 3, so that's here. 5 is 0, 1, 0, 1, so here's 0, 1, 0, 1, so there's 5, I think. Yeah. Then 7 is 0, 1, 1, 1, so here's 0, 1, 1, 1, so there's 7. And 6 is 0, 1, 1, 0, 0, 1, 1, 0, that's here. So there's the 6. What do we need here? I was doing them in sorted order for some reason and then went out of order. Okay, so we need 8 still and 9 still, I think. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Yes. Okay, so we need 8. 8 is 1, 0, 0, 0. That's here. And 9 is 1, 0, 0, 1. All right, so there's Jenny's digits as minterms in our Karnaugh map. Now, we don't want anything from the circuit AC or DC to ever happen. So we're going to say that's going to be physically impossible, unless, of course, it is also one of Jenny's digits. So AC, the product, is A is a 1 and C is a 1. So A is a 1 in the bottom 2 rows. C is a 1 in the right 2 columns. So that's these 4. We're going to mark those with X's. All right, now we got to do DC. So DC means D is a 1 and C is a 1, or it should have been in the other order, but it has to relate to the band. So D is a 1, C is a 1. That's this column. So this whole column should be physically impossible unless it's one of Jenny's digits. So we actually already have those marked off. So the rest of these then are 0. All right, so why do we have these physically impossible ones? Well, because this happens with some regularity in designing circuits to be part of a specific system, particularly embedded systems, right? So it's possible that you have situations where some particular set of input values just can't occur, either because equipment just doesn't allow it, or you have to purposefully dampen it beforehand because it would cause some catastrophic situation. Right? So this is not uncommon. But the value comes in for us because if it can't possibly happen, then we can pretend that those X's are 0s if we want, and then just do our normal ones looping on the ones that we already have. But if we could utilize those X's to make bigger rectangles so that our expression in the end is simplified, we can pretend any one or more of those X's are 1s. So we can loop X's with 1s. And that will allow us to shrink, by making bigger rectangles, shrink the size of our simplified expressions. So let's do that here. Let's see, what do we got? Well, this bottom row is 4. It utilizes some X's, which is great. Otherwise, we would have just had these 2 by themselves. Let's see. We've got, with this one up here, we can connect him to 4 as well. I should be using some different colors. Why do I have all these colors if I don't use them? This one can be grouped with this one, but not extended all the way to here, because that's only an area 3. So I'm going to mark that here. So that's a size 2 rectangle. I've got this one left, and I can group it with him, I can also group it with these two folks down here. So I can get a size 4 rectangle, which is extra great. Then I only have this one fellow left. I can loop him by himself, but with wrapping vertically, I can actually get this thing to be a slightly bigger size and still be a power of 2 in area. And now we will solve our soft rock circuit. What do we got here? Why? That's a good question. Why? A, B, C, and D. And let's see here. Which will we start with? Horizontal blue. That happens when A is a 1 and B is a 0. And C and D don't matter because it goes across all columns. For the obelisk blue one, A and B won't matter because it crosses all rows. But C needs to be a 1 and D needs to be a 1. How ironic that DC ends up in our final expression. C is a 1, D is a 1. It's so perverse. I've written backwards. Let's see. Green square. For that one, A goes to 0 or 1 between these two rows. So we throw A out. B is 1 all the time, so we want B. And we want it to be a 1. For the columns, in these two columns, C is a 1. And D switches values, so we don't want it. So we get rid of it. Remember, the inversion bar indicates a 0. No inversion bar indicates a 1. Let's see. 1, 2, 3. We need the red one. This red one is A is a 0 and B is a 1. A is a 0. B is a 1. C is 0 or 1, so C doesn't matter. But D needs to be 1. And then the last one that we have is the green one that wraps around vertically. In this one, A is a 0 or 1 in these two positions, so we get rid of A. But B is a 0. C and D are always 0, so we can mark those. C invert, D invert. And we have our soft rock function. So utilizing the Karnaugh map, we can fairly simply simplify functions. And then when we combine that with the other technologies, like the way the sum of product min-term form works, we're also able to just describe a function in terms of what it should, when it should output a 1 or when it should output a 0, and even when certain input patterns will never happen or be physically impossible. And then we can pretty simply come up with a simplified circuit.